What do this automatic packaging machine and this lock have in common? Let's take a look. Huge forces are required to open and close the lock gates. Force is required in two directions. Hydraulic drive is the right solution. The lock gates and the control room are far apart. This means that control signals have to be transmitted over a large distance. But a hydraulic pipe is not suitable for this. Electrical control signals, which travel via electrical cables, are the right solution here. In the case of these complex automatic assembly machines, it is not distance that is the primary argument against pneumatic control of the valves. In this case, it is the many control functions required in order for the entire complex program to execute. Here too, electricity has been selected for signal transmission, because it is simply more manageable. And because electricity is a prerequisite for the use of electronic open and closed loop control systems. And it allows the system to be linked to the company's data processing system. In that case, why use pneumatics at all, if electricity is there anyway? Well, pneumatics drives allow linear motion to be achieved much more simply. And fast cylinder speeds can be achieved, resulting in short cycle times. In these examples, the control energy is not the same as the work energy. That is why they are called electro-pneumatics and electro-hydraulics. These are so-called hybrid systems. Let's take a look at the structure of circuits with different types of control. Here we have the manual operation of a directional control valve as a final control element. In the pneumatic control, there is a clear differentiation between the control part, left, and the power part, right. Here the signals are generated and logically associated in the pneumatic control part, and the final control element is pneumatically actuated. In a corresponding electro-pneumatic control, there are electrical signal elements in the control part. In this case, signal processing is not carried out by a special device, but by connection of the various signal elements in such a way as to produce the function. The directional control valve, or more accurately, the solenoid valve, is now actuated electrically. This type of control part can, of course, also be used to control the hydraulic power part. Then we have an electro-hydraulic control. Now let's take a look at what happens in practice. The elements of the control part are, of course, distributed throughout the entire system. The signal elements, here the push buttons for operation, the sensors, and the solenoid switches on the pneumatic cylinders send electrical signals to the machine controller. From there, the solenoid valves are controlled. So here we have the interface between the electrical signal part and the pneumatic control part. Also in the elevator, these two areas are clearly differentiated. The controls in the elevator and on the door and the sensors in the shaft, which report the position of the elevator, together with the controller, form the electrical control part. The solenoid valve is the interface to the power part, consisting of the power pack, the valve in its function as a final control element, and the hydraulic cylinder. These systems also demonstrate why hybrid systems are used. For the large distances involved in the lock, electrical lines and electrical control energy are of course much more economical than a hydraulic control system. And in the case of complex machines like this automatic assembly machine, it is not only the many control lines and controllers that speak for an electrical control part. The logical association of this huge volume of signals is only feasible with an electronic controller. So here we have a complex example of an electro-pneumatic system. And in the case of the elevator, the power part requires huge forces, which is naturally not the case for the control part. So here too, a hybrid system is the right solution, electro-hydraulics. Yet another advantage of a system with an electrical control part. If electricity is available at the machine anyway, monitoring elements and indicators such as buzzers and lamps can be cheaply and easily integrated. And of course, the power part can be supplemented with electrical drives, such as an electric motor. In electro-hydraulic systems, electricity is also found in the hydraulic power supply part. The hydraulic pump of this power pack is electrically driven. Electricity. We take it for granted. We cannot imagine modern society without it. From the coffee machine to the computer, from the lamp to industrial plant, nothing works without electricity. But what is electricity? Let's make a comparison. In pneumatics, air is the source of energy. In hydraulics, it's oil. In electricity too, there's an energy source, but it's invisible. It's called electrical current, or more precisely, the electron current. There are three terms that everyone knows that define an electric current: voltage, current, and resistance. Voltage has the symbol V and is measured in volts. A rating plate on all electrical devices indicates with which voltage the device is to be operated. The current has the symbol I and is measured in amperes. The rating plate also indicates how much current a motor consumes. And finally, the resistance has the symbol R and is measured in ohms. This value indicates the resistance with which a load opposes current flow. These three variables are mutually dependent, and this can be expressed with a simple formula. V equals R times I. In other words, voltage is resistance times current. Or more practically, current equals voltage divided by resistance, because normally the voltage is given. And the whole thing has a name, Ohm's law. An experiment to demonstrate. The white lines indicate electrical lines. The voltage V is 24 volts. The lamp has a constant resistance of R and as we see, a current of 84 milliamperes flows. If we double the resistance by adding a second lamp, the voltage at the source is still 24 volts. But the two loads connected in series have divided the current according to their resistance. So we have 2 times 12 volts. Because the current is also halved, namely to 41 milliamperes, the two lamps do not glow as brightly as the single lamp did. That is the disadvantage of this series circuit. As we can see, the parallel circuit is different. As each lamp is practically connected directly to the voltage source, the full voltage is applied to each load. And the full current flows through each lamp. Both glow brightly, as did the single lamp at the beginning of the experiment. For this reason, loads in electrical systems are normally connected in parallel. We have already said several times that current flows, but why does it flow? From where to where? Let's take a rechargeable battery as a voltage source. It has two connections, or more correctly, two poles, a minus pole and a plus pole. If we now connect a load to one pole, nothing happens. The lamp does not go on until we connect the other line to the second pole, because the current cannot flow until the circuit is closed. It does not matter how the lamp is connected. It goes on regardless of which way it is connected to the poles of the battery. The decisive thing is the potential difference between the poles. But why does the lamp illuminate, and why at different levels of brightness? Here too, Ohm's law provides the answer. The filament of the lamp has a resistance which we will assume to be constant. When a current of 12 volts is applied, a voltage of 41 milliamperes flows. Because of the frictional resistance, the filament is heated by the flow of electrons to such a degree that it begins to glow. If we increase the voltage to 24 volts, the current also doubles to 84 milliamperes. In other words, twice as many electrons are forced through the filament, and it gets even hotter. The lamp glows brighter. A word about electrical power. Here the same voltage is applied to both lamps, but one glows brighter than the other. The reason? Their power consumption is different. The less bright lamp is a 25-watt lamp, through which less current passes than through the brighter 60-watt lamp. The watt is the unit of measure for electrical power, and is the product of voltage times current. All electrical loads that work according to this principle and produce light and heat are called resistive loads. And here is a phenomenon that everyone knows, the short circuit. What happens exactly? If in an experiment we connect both poles of a voltage source directly, an extremely large current flows because there is no resistance. The result, extreme heat which leads to melting of the conductor or other damage. The solution? Fuses are integrated into electrical circuits. The fuse then interrupts the current flow and prevents further damage. So far, we have looked at two effects of electrical current, namely, light and heat. Another important effect is the magnetic effect. When a current flows through a conductor, it generates a magnetic field, the strength of which is proportional to the current. If the conductor is coiled, the magnetic field inside the coil is amplified considerably. Now the strength of the magnetic field is dependent not only on the current, but also on the number of turns in the coil. The more turns, the stronger the magnetic field. If a soft iron core is inserted into this air core coil, the electromagnetic force is amplified considerably. This is the principle on which solenoids are based. Another phenomenon. If the soft iron core is movable, it is drawn into the middle of the coil when current is applied, thus producing a magnetic field. In this way, the core has the function of an armature. We will take a close look at this specific effect in the section on solenoid valves. The magnetic effect of current is the form of electrical energy most often encountered in electro-pneumatics and electro-hydraulics, in relays, contactors, and solenoid valves. In contrast to resistive loads, these are called inductive loads. The electric motor also belongs to this category. A few words on the danger of electrical current. It is imperative that safety regulations be observed. Contact with live parts can be dangerous, even fatal. A short circuit can, as we have seen, have nasty consequences, a fire or a damaged system, for example. And then an important basic rule. Only authorized specialists should make changes to electrical systems, and, of course, only when it has been isolated from the power supply. Other protective measures. High voltage cables are laid in such a way that no contact with them is possible, or so that no voltage can jump across. And current carrying lines are insulated. And finally, low voltages are used wherever possible. That's all on the fundamentals of electro-pneumatics and electro-hydraulics, in which various media, electrical current as the medium for control energy, and hydraulic oil or compressed air as the medium for actuation energy, complement each other ideally. We are constantly receiving signals to which we react, and sending out signals to influence our environment. Signals in technical systems have the same function. They have some effect somewhere in the system. In electro-pneumatics and electro-hydraulics, the medium for signals is electric current. The signals are generated by closing or opening an electrical circuit, either allowing or interrupting the flow of electric current. In other words, in the broadest sense, all elements for signal generation are electrical switches. Electrical signals are triggered by an external influence on a switch. The basic components of a switch are the contacts. If the contacts are closed by operation of the switch, it is a normally open or make contact. This is a symbol used to represent it in circuit diagrams. If the contact opens when the switch is operated, it is a normally closed or break contact, which has this symbol. If operation results in one circuit being opened and the other closed, we have a changeover contact, which has this symbol. The many different types of actuation for switches give some idea of the wide range of signals they can generate. Let's look at a normally open contact as an example. First, manual actuation. The contact only stays closed as long as the button is pressed. This is a push button, and this is the symbol for it. If the contact remains closed, it is a switch. This is shown in the symbol by a detent. The contact does not break until the switch is actuated again. This limit switch is an example for automatic mechanical signal generation. Here it is used for interrogating position. It automatically closes the circuit when the piston rod actuates the roller lever. The small circle is the symbol for mechanical actuation by means of a roller lever. This proximity switch has a contact that is magnetically actuated. Its uses include position interrogation on pneumatic and hydraulic cylinders. A permanent magnet on the piston attracts the movable contact tongue. The circuit is closed. Here too, a permanent magnet on the cylinder triggers a signal. Its magnetic field influences the field of an inductive sensor. The electronic circuit detects this change and opens or closes the circuit. Inductive sensors are not only actuated by a magnetic field, they detect all electrically conductive materials that come within range. This property is used for non-contact position or status interrogation. Another non-contact proximity switch is the capacitive sensor. It detects non-conductive materials that enter and influence its electrical field. This change is analyzed and translated into a switching operation, that is, an electrical signal. And finally, light can trigger signals. In optical sensors, the interruption or reflection of a light beam is converted into an electrical signal. Switches that are actuated by pneumatic or hydraulic pressure are called PE transducers or HE transducers. In this example, a diaphragm in the device actuates a micro switch when a preset value is reached. This results in an electrical signal. An example: the light is to go on when a certain pressure is reached. This is the symbol for a pressure switch in a pneumatic or hydraulic circuit diagram. And this is the electrical symbol. And here is how it works. The pressure is exerted on a diaphragm or a piston. When an adjustable preset pressure is reached, a micro switch is actuated which closes the circuit, thus generating an electrical signal. If the pressure drops, the switch automatically opens again at a certain pressure. The difference between the switch on point and the switch off point is the hysteresis of the pressure switch. This varies according to the pressure range. The hysteresis is caused by the frictional resistance in the components of the switch. It is important to know the hysteresis of a switch because it switches at different points for rising or falling pressure. The differential pressure switch is a special type of pressure switch. One application is the monitoring of the contamination of an oil filter in a hydraulic pressure line. This is done by tapping into the lines upstream and downstream of the filter. The pressure differential is a measure for the contamination of the filter. independent of the effective pressure level. A differential pressure switch has two pressure chambers, separated by a metal diaphragm. If the pressure in the upstream chamber rises because of increasing contamination of the oil filter, an increasingly large pressure differential results between the two chambers. This causes the diaphragm to bend. This in turn pushes a pin into the field of an inductive sensor, and an electrical signal results. All signal elements we have looked at here have one thing in common, whether a manually actuated switch, a sensor, or a pressure switch. It is always an external influence that triggers the electrical signal at the signal element, causing the circuit to be opened or closed. Electromechanical signal processing is primarily undertaken by relays or contactors. The relay consists of the coil, the magnet core, the armature with the contacts. When a current flows through the coil, a magnetic field is produced and the armature picks up. The relay switches. A contactor works according to the same principle, but it is designed to switch power circuits. Back to the relay. How the relay processes the control signal depends on the type of contacts and how these are connected. Relays can be equipped with several contacts, normally changeover contacts. This means that one control signal can cause several circuits to be opened or closed simultaneously. Here, for example, the relay is connected in such a way that it has one normally open, one normally closed, and one changeover contact, although the relay actually has three changeover contacts. You can see that pressing the button results in three different simultaneous actions. In pneumatics, solenoids of 0.5 to 12 watts are used. In hydraulics, solenoids range from 12 to 50 watts. As a result, valves have to be controlled indirectly via relays. Special types of relays have other functions in addition to the circuit switching function, counter relays and time delay relays. This pickup delay relay does not switch until the control signal has been present for a preset time. This time is adjustable. The elevator door is an example. When it is closed and the door contact gives a signal, there is a pause before the elevator is set in motion. The dropout delay relay works the other way round. When the control voltage in the coil is interrupted, there is a pause before the relay drops out. Here's one in a car. The door contact interrupts the control circuit, and the light goes out after a short pause. Counter relays switch circuits when a certain number of counter pulses has been reached. This number can of course be set. They are used, for example, when a step is to be repeated a number of times before the next step is started. The hydraulic cylinder is not to be actuated until the pneumatic cylinder has extended and retracted 3 times. Here the relay counts the pulses from the cylinder limit switch. The relay does not switch the solenoid valve for the other cylinder until the preset number of pulses has been reached. Electromagnetic signal processing by relays is part of the topic hardwired programming, which is covered in a separate section. In electro-pneumatic and electro-hydraulic systems, the electrical signals in the control part have to be converted into actions by the pneumatic or hydraulic power part. This is achieved with solenoid valves. In their function as final control elements, they are no different to normal pneumatic or hydraulic directional control or way valves. The difference is the way they are actuated. Solenoid valves are electrically controlled, so this is a so-called electro-pneumatic transducer. An electrical signal brings about a pneumatic action. The same in electrohydraulics. An electrical signal is converted into a hydraulic action. This hydraulic 4-stroke two-way valve clearly demonstrates the function of a solenoid valve. Switching from the initial position takes place as follows. On one side of the valve is a solenoid. Its core acts as an armature, exerting a force on the control piston of the valve. If the coil is energized, an electromagnetic field is produced. The armature is pulled against a spring to the middle of the coil. As a result, it pushes the control piston of the valve into the other switch position. The valve remains in this position as long as the electrical signal is present. When the current is interrupted, the magnetic field, and therefore the magnetic force, collapse. The return spring pushes the control piston and the armature back into the initial position. Here it is in practice: a push button, a solenoid valve, and a hydraulic cylinder. The signal is given. The cylinder extends. The LED indicates that current is flowing, that is, that a signal is present. Only now does the cylinder retract. These are the symbols. On the hydraulic side, the cylinder and the 4-stroke two-way solenoid valve. On the electrical side, the push button and the solenoid valve, but shown differently, namely as an electrical symbol. As we have seen, in this circuit the directional control valve remains switched as long as the electrical signal is present. Not the case here. A short switching pulse is sufficient to switch the valve, causing the cylinder to extend. Nothing else happens, so in a sense the signal is stored. The valve does not switch back, causing the cylinder to retract, until a counteracting pulse energizes the other coil. Then the valve switches back and the cylinder retracts. We can see that there is a second push button and that it is a different valve. The difference is that this 4-stroke two-way valve does not have a return spring. Instead, it has a second solenoid. The valve is switched back and forth by a pulse for each direction. That is why it is called a double solenoid valve. If two pulses are present at the same time, this valve stays in the position it is already in. The current position is dominant. In hydraulic valves, the oil stream can result in considerable lateral forces that could change the position of the control piston. This is prevented by mechanical detenting of the switch position. The lock makes the significance of signal storage clear. One short press on the push button, a short signal, is sufficient. The cylinder extends to its end position, although the signal is no longer present. Switching of directional control valves means overcoming spring forces, friction, lateral forces and seating thrust. This requires solenoids with sufficient power. And to ensure safe functioning of the solenoid, the heat generated by the coil has to be limited. The solution: the solenoids used are kept as small as possible. In order to nonetheless achieve the required force for switching large directional control valves, the energy of the compressed air or hydraulic oil is used to switch the valve. This process is called pilot control. This pilot-actuated spring-return 5-stroke two-way valve demonstrates the principle clearly. A channel in the valve branches from the pressure line to a spring-loaded poppet. If the solenoid is energized, the poppet is raised and compressed air can act on the control piston of the valve, which switches against the pressure of the return spring. What is the sense in all this? It requires considerably less magnetic force to open the control channel for the compressed air than for the solenoid to switch the control piston directly against the force of the return spring. Pilot-actuated double solenoid valves are also used. In electro-pneumatics, pilot control is used to allow solenoids with minimum possible power to be switched by an electronic controller. In electro-hydraulics, only larger directional control valves are pilot-actuated, and these are driven electrically via a relay or contactor. The reason? Smaller solenoids are cheaper, and the solenoid valve is cheaper overall. There are two types of pilot control. The pilot valve switches the power valve either with the aid of the normal working pressure or the hydraulic oil, or with a separate lower pressure that is supplied via a different port. The latter method results in smoother switching of the directional control valve. Solenoid valves are normally equipped with a manual override. This allows the valve to be switched not only by the control signal, but also manually. Here, a screwdriver is being used. The manual override is used during setup of the system or for testing the function of the valve. The symbol indicates how the valve is actuated. Take the 4-stroke two-way valve, for example. This is the symbol for a spring-return solenoid valve. This is a pilot-actuated solenoid valve. This shows manual override. And in the case of the double solenoid valve, the return spring is replaced by these symbols. The design and function of all industrial systems and machines are documented in circuit diagrams. This is essential for installation, maintenance and repair. In electro-pneumatics and electro-hydraulics, two circuit diagrams are used. One for the pneumatic or hydraulic part, and one for the electrical part. The function of this electro-pneumatic slide unit is simple. When the optical sensor signals that 5 packages are present, the piston extends. When it reaches the extended position, the valve is reversed and the piston retracts. As only one condition needs to be fulfilled for each action, the valve can be directly controlled by the signal element. The circuit diagram of a comparable pneumatic power part shows the double-acting cylinder and the 5-stroke two-way double solenoid valve. And this is the corresponding electrical circuit diagram. You can see two 24-volt circuits. To simplify the diagram, the circuit diagram does not show the voltage source, in this case the power supply unit. If push button S1 is pressed, coil Y1 is energized. This switches the valve and the cylinder extends. In its forward end position, the piston actuates the limit switch S2. This closes another circuit, energizing coil Y2, reversing the valve. The cylinder retracts. When the valve is directly controlled in this way, control circuit and power circuit are identical. This diagram shows indirect control of a valve via a relay. When in the first circuit contact S1 of the push button closes, the coil of relay K1 is energized and contact K1 in circuit 3 is closed. Coil Y1 is energized and actuates the valve. The cylinder extends and actuates limit switch S2 when it reaches its forward end position. Coil Y2 is energized and reverses the valve. The cylinder retracts. If an optical indication is desired that the signal for extension has been given, a second normally open contact of the relay is used. The indicator lamp is switched on by the second contact K1. The individual elements are given designations for identification. This creates a link between the electrical circuit diagram and the pneumatic or hydraulic circuit diagram. By the way, the positions of centers are indicated by a line. As you can see, the circuit diagram is divided into two parts. The left part shows the circuits for signal input, and the circuits on the right show the signal output and the effect. Using this principle, the function and sequence of even the most complex systems can be documented clearly and unambiguously. This is a hydraulic device that operates according to this principle. The larger dimensions involved mean larger solenoid valves and switching of larger currents. This requires indirect control of the valves via relays. Hardwired controllers are systems in which the sequence and the functions are determined by appropriate fixed wiring of the individual elements of the control part. Electrical lines are primarily conductors for electric current, but the arrangement of the various elements and the way they are connected determines the function of the system. Changing the program sequence requires a change to the wiring. The pin assignment of a relay determines the logical function. In the case of a normally open contact, input signal at the coil leads to output signal at the contact. That is logical function identity. In the case of a normally closed contact, input signal at the coil leads to no output signal at the contact. That is negation, or a logical knot. In this elevator, we can see hardwired logical associations for the control of the hydraulic power part. The elevator only travels when the push button has been pressed and the elevator door has closed. This is a logical AND. And this is how it is shown in the circuit diagram. If the two switch elements with their normally open contacts are connected in series, current can only flow when both contacts are closed. This is an AND function. Push button and door contact. This is another logical association. The elevator can be set in motion from inside or from outside. The circuit diagram again has two normally open contacts, but this time they are connected in parallel. It is sufficient from one or the other to be closed in order for current to flow. This is a logical OR. Electrical signal latching is needed when spring return valves are used, because in this case the signal must remain present as long as the valve is to remain in the switched position. In addition, the position can be indicated by a signal lamp. This requirement can easily be met with a self-latching relay. When push-button S1 is pressed, relay K1 picks up and the two contacts K1 close. One keeps the relay coil energized and the other switches current to the solenoid valve. This means that the relay remains in this position, even if contact S1 is opened, until S2 is opened. If S1 and S2 are actuated simultaneously, the relay coil remains energized. This is called a dominant ON latch. An example. In this circuit, the ON signal remains effective even if the OFF signal is given at the same time. This means that the machine step is automatically completed once started. This is another latch circuit. But in this case, the OFF push button S2 is not connected in parallel as before, but in series to push button S1. This means that the circuit is interrupted if S2 is pressed, regardless of the position of S1. This is called a dominant OFF latch. Here, the cylinder retracts immediately if the OFF signal is given, even if the ON signal is still present. Machines may require this kind of latch for safety reasons. The function of the wiring of this hardwired machine can also be undertaken by a programmable logic controller, or PLC. In this case, the logical association and processing of signals takes place here. The functions in the marked area of the hardwired circuit are now undertaken by the PLC. A PLC consists essentially of three parts: the signal input part, the central control unit, and the signal output part. The central control unit consists of a processor and program memory. Here an example. At the end of a conveyor belt, a proximity switch detects whether a valve is present or not for the next step of the process. If a valve is present, a signal is given to a terminal. This signal is passed via the terminal to the input module. The input module converts this signal so that it can be processed by the central control unit, a small but powerful computer. In the central control unit, the signal is processed by a stored program, and an output signal results, which is passed to the output module. There it is amplified and conditioned, and then passed via a terminal to the solenoid valve. This switches and causes the cylinder to extend, so that the gripper can pick the valve from the conveyor belt. The program for the PLC is normally written on a PC with the aid of special software and then loaded into the controller. The PLC is the ideal controller for electro-pneumatic and electro-hydraulic systems. It combines high reliability and small space requirement with simple operation and exceptional versatility.